This is chapter 4, lesson 1 on trigonometric ratios, which for us is a review because we looked at this stuff in 10-3, so I will be going through these lessons a lot faster. Trigonometry is a branch of math that deals with angles, triangles, and trig functions such as sine, cosine, and tangent. So what we're going to do in this unit is study the relationship between sides and angles in right triangles. So I asked you guys to start working on the first investigation and measuring the side lengths of each of these. So we had A1 to B1 was 1.4, O to A1 was 2. In the next triangle, O to A2 was given to us as being 4 centimeters. What was the length of A2 to B2? And when I go 2.8 divided by divided by 4, what do I get? 0.7. Okay. What was the length of A3 to B3?
4.1 over 5.9.
Okay, say that again.
4.1 over 5.9.
And what did that equal?
0.7.
Okay. And what about A4 to B4?
5.6.
And 0 to, or O to A4? And when I divided that, what did I get?
0.7.
So what we can do is we can reach this conclusion that the ratio 0.7 somehow connects itself to this 35-degree angle, because in each of these we were starting off, this was my triangle, it was 35 degrees. This was my triangle, 35 degrees. This is my triangle, 35 degrees, and so on. So now what I want you to do is work through investigation number 2. So what you're going to do in investigation number 2 is we're measuring A1 to B1 and then O to A1. So the same thing as we did before. So what measurement did you get for A2 to B2? And if I go 4.8 divided by 3, what do I get?
1.6.
Okay, A3 to B3.
7.2.
And 0 to, or O to A3.
4.5.
And when I divide them,
1.6.
A4 to B4.
9.6.
And O to A4.
6.
And when I divide them,
1.6.
so in this case, we have that this ratio of 1.6 somehow connects itself to 58 degrees. So let's look at the size of a triangle. We let angle AOB be angle X. So we can label angles 2 different ways. We can label them by a single letter, although we generally try not to do that. We could label the angle itself, this is angle X, or we could use the vertices to spell it out. And when we use the vertices, the angle that we're looking for always comes in the middle. So it's angle AOB, or it could be angle BOA, as long as the O comes in the middle. So in relation to this angle X, we can label the other 3 sides. First of all, we have the hypotenuse. Hypotenuse is always the longest side of the triangle, which means it's always across from the 90-degree angle. This becomes my hypotenuse. The other 2 sides, which we call the opposite and the adjacent, depend on where angle X is. So if I'm talking about the opposite side, it is opposite to this angle. Opposite. That is opposite to this angle. If we are talking about adjacent, adjacent means next to. So adjacent to angle X would be the side OA. So using that information, I want you to complete class example number 1, labeling the triangles as hypotenuse, opposite, and adjacent. So in triangle DEF, which side length do I label as hypotenuse? FE. Which side would be opposite? and then the last one would be adjacent. Okay, so if we look at angle STV, which side length is the hypotenuse? VT. Opposite,
VS.
and then adjacent would be ST. So on the previous page, when we were looking at those ratio relationships within our 35 and our 58 degree angle, what we found was, if I go back to this page, these measurements were the opposite side of the triangle to the adjacent side of the triangle. So the opposite to the adjacent always gave me the same ratio for that 35 degree angle, and did the same thing in my 58 degree angle. This is called the tangent ratio. So we did this last semester. We got these three trig ratios. We had that sine was the opposite over the hypotenuse. Cosine was the adjacent over the hypotenuse. And tan was the opposite over the adjacent, which gave us our SOHCAHTOA. Now, with these three trig functions, they're called primary trig functions. They're secondary trig functions, or what we call reciprocal trig functions. If instead of going opposite over hypotenuse, I went hypotenuse over opposite, I would get a cosecant ratio. If I went hypotenuse over adjacent, I would get secant. And if I went adjacent over opposite, I would get cotangent. These we don't look at this year in depth, but it is good to know that they exist. And the key to think about the matching between them, co appears only once in each set. So we have sine and cosecant, cosine and secant, tangent and cotangent. So I would never have, or I don't have, or try not to get mixed up thinking which one does secant match to. Secant can't match to sine. It has to match to a co. Sine can't match to either cotangent or cosecant because cosine can't have another co with it. And tangent and cotangent have the same name, just the prefix of co. So if we look at class example number 2, it says use the diagrams in class example number 1 to list the sine ratio, cosine ratio, and tangent ratio for angle x. So if we looked at that triangle DEF, that was the triangle we're looking at. So I'm going to quickly sketch it here. It was triangle DEF, and this was angle x. So if I'm looking at using the sine ratio, which was opposite over hypotenuse, I would label it as side DE over side DF. If I was looking at the cosine ratio, which is adjacent over hypotenuse, it would be DF over EF. And then the tangent, being the opposite over the adjacent, would be DE over DF. And if you wrote down ED over FD, it would still be correct. So the other triangle in question B looks like this. I've got that totally messed up. Doesn't even look like a right triangle. Try that again. There's my angle X. So using those letters, I want you to take a moment to write down what the trig ratios would be. So now if I look at class example 2b. The sine ratio would then be what letters? Be SV over TV? Yes?
Yep.
Okay, and cosine would then be,
ST over VT.
and the tangent ratio.
VS over ST.
Good. So let's look at class example number 3. In class example number 3, we actually have numbers. So if the sine ratio is the opposite over the hypotenuse in terms of numbers, it's 20 over 29, which according to my decimal gives me what to the nearest thousandth? 3 decimal places.
0.1.
20 divided by 29? No, don't press the sign. It's just 20 over 29.
Space?
Yeah. So what do you get?
0.689.
6896. So then this would round up to 0, which would then round this up to 9, right? So you get 0.690. Okay. When you're putting this into your calculator, it's just 20 divided by 29, not sine. It's just 20 divided by 29. So the cosine ratio, which is the adjacent over the hypotenuse, what is the length of my adjacent side?
0.7.
That would be the ratio. What's the length? How long is the adjacent side?
21.
Okay, and the hypotenuse was 29,
Yeah.
and you said that was 0.724, thank you. And then the tangent ratio is opposite over adjacent. So what's the length of the opposite side?
20.
And the length of the adjacent side?
21.
Which gives me 0.952.
952.
Okay, let's take a moment to talk about these ratios. If my sine ratio is opposite over hypotenuse, what do I know about the hypotenuse of my triangle? It is always going to be the longest side, which means this number here is always going to be bigger than the top. We call that a proper fraction. And when I go to divide this, I'm always going to get a number that's going to start with 0 point something. I will never get a 1 point something for sine. I will never get 1 point something or 2 point something for cos either. Could I have a number bigger than 1 for tangent though? Yeah. Could my adjacent side be, could my opposite side be longer than my adjacent side? Absolutely. In this triangle, if I went with angle N and I went opposite over adjacent, I would have that exact scenario. So tangent can be greater than 1, but sine and cosine will never be greater than 1. So I want you to practice with question 2 and 3, and then I'll move on to the next part.